In this video, we're going to have a brief look at some complex analysis. The theory of calculus is called analysis. Real analysis concerns the theory of calculus and related concepts as they apply to real valued functions of a real variable. In other words, the kind of functions that we've been studying thus far in Calculus 1 and 2. Complex analysis concerns the theory of calculus and related concepts as they apply to complex valued functions of a complex variable. We can generalize many calculus concepts to allow them to be used with complex numbers. And we're not going to do much with this in Calculus 2, but there is an important basic connection to series that you might find interesting. First, recall that a complex number is a number of the form a plus bi, where I is the principal square root of -1, and a and b are real numbers. So if you think about this, if b is 0, then this part goes away, and we get a, which is a real number. So real numbers are a subset of the complex numbers. If the a is 0 and b is not 0, then you get numbers of the form bi, which are the imaginary numbers. And then things like 2 plus 3i is neither real nor imaginary, but it is complex. And here's a Venn diagram of some of the number systems, some of the basic numbers that we have. So if we start with the natural numbers, which are given by a open-faced n like this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, so forth. Those are the counting numbers. We have those. Most ancient cultures had something like that. A later addition was the whole numbers to add 0 to that list. Okay, and then if we want to be able to do undo addition, when able to do subtraction, this is going to lead us to the integers, which are Zahlen in German. So this Z here is for those, and that includes the natural numbers, the whole numbers, and their opposites. Now, if we want to be able to do multiplication, we're fine within the integers, but if we want to undo multiplication, this leads us to division, which leads us to rational numbers, which are quotients, Q for quotient, of numbers of the form P over Q, where P is an integer and Q is a natural number. Or you could have them both be integers, but just make sure Q is not 0. And it turns out this is equivalent to repeating or terminating decimals. Now, we still don't have a solid number line yet, right? We started with the natural numbers. It's just these dots, nothing in between. We put in 0, then we have the integers, so now our dots go both directions, but we still haven't filled in. The rational numbers fill in quite a bit of this, but if we want to fill in all of that, we need more numbers. We need the real numbers. So one way to think of that is all decimal numbers, terminating, repeating, or non-terminating, non-repeating decimals. Okay, so those are the real numbers. They include the irrationals, so we'll use an H for that, and the rationals. The imaginary numbers are numbers of the form bi, where b is a real number but not 0, and I is the square root of -1. And the complex numbers include the reals, imaginaries, and other things. All this, which is numbers of the form a plus bi, where a and b are real, and I is the square root of -1. Now, one of the first things that we might do is we might look at powers of I. And that's interesting. If we raise I to integer powers, we always either get 1, I, -1, or -I. So if the power is a positive integer, then we can just divide the power by 4 and replace the power by the remainder. And the reason that is because of this cyclic pattern here. I to the 0 is 1. I to the first will be I squared is -1. I cubed would be I times I squared, so that'd be -1 times I is -I. I to the fourth would be I squared times I squared, which is -1 times -1, it's back to 1. And then we see that we start getting a cyclic pattern, right? So I to the fifth would be I to the sixth is -1, I to the seventh is -I, and so forth. So if the power is congruent to 0 mod 4, we get 1. The power on I is congruent to 1 mod 4, we get I. If the power on I is congruent to 2 mod 4, we get -I, -1. And if it's congruent to 3 mod 4, we get -I. So if we have a long power like this, we can just divide by 4 and look at the remainder. It's even easier than that because um, we know 100 is divisible by 4. So really all we have to do is take the last two digits and divide by 4. So this is going to be the same as I to the 67th. Divide that by 4, we get a remainder of 3. That's going to be the same as I cubed, which is just uh, minus I. And we could do basic arithmetic, such as addition, subtraction, multiplication, and division with these, but we simply treat the complex numbers just as you would polynomials, but just remember that I squared is negative 1. So 3 plus 2i plus 5 minus 6i, you just add the real parts, 3 and 5, to get the real part here of 8. And you add the imaginary parts, 2 and negative 6, to get negative 4 for the imaginary part here. So you end up with 8 minus 4i, just like you would if they were polynomials. Same way here, you can distribute the minus here and then add, regroup 3 plus 2i minus parentheses 5 minus 6i is 3 plus 2i minus 5 plus 6i. Then add the negative 5 and the 3 to get negative 2. Add the 2 and the 6 to get 8. And that's I for the I part. Just use the distributive property here, also sometimes known as FOIL, for multiplying these. 3 times 5 is 15. Outer one, 3 times negative 6i is negative 18i. Inner product, 10i. Outer product is negative 12i squared, but I squared is negative 1. So this becomes plus 12 plus the 15 is 27 minus 8i. So you see you always get something back in that a plus bi form. If we're going to divide, then what we do is we multiply top and bottom by the conjugate, complex conjugate of the denominator. So we have 3 plus 2i over 2 minus plus 6i. Multiply the top and bottom by 2. Well, that's plus, so now you make it minus. And we're using this pattern, a plus b times a minus b is a squared minus b squared. In the bottom, let's just look at the bottom for a minute. So 2 squared is 4. Negative 6i squared is 36i squared, but I squared is negative 1, makes that negative positive. So this rational makes the bottom a real number, 40. It's kind of like when we rationalized things with square roots in them. Okay, that binomial, one of them being a square root. In the top, we do FOIL. 3 times 2 is 6. Here we get 4i there. Here we get negative 18i there. And here we get negative 6i squared. I squared is negative 1, so this is plus 12. Plus that 6 is 18. The negative 18i plus 4i is negative 14i. And then if we want an a plus bi form, we just distribute this 40. 18 over 40 minus 14 over 40i. And then reduce those fractions if we can. In this case, we can cancel a 2 out in both cases, so we get 9/20ths minus 7/20ths I. Now we can also graph these things, okay? And the way you graph these is in what's called the complex plane. You have the real axis, which is the numbers. The real numbers are on this, what the horizontal axis, normally we call it the x-axis. It's the real axis here. And what's normally thought of as the y-axis, the vertical axis, is the imaginary axis. So that point right there on the y-axis is I, and this is 2i and 3i and negative 1i. And these are all imaginary numbers except for the origin, which is real. And if you're on this axis, it's a real number. But then if you have numbers that are not real or imaginary, but they're complex, they're points in the plane. So the number right up here at the point 4,3 is 4 plus 3i. So in that way we can graph them. And so notice we have a nice little relationship here, Pythagorean relationship on this right triangle. So this side is A, this side is B, or this x is A and the y is B. The distance from the origin is the sometimes called the modulus or the norm or the magnitude of that complex number, which is I'm also going to call r. It's the radius of a circle that would go out that far. And this direction angle is theta here. And so we have a basic relationships among this, that a squared plus b squared equals r squared, And they got basic trig ratios like sine of theta is b over r, um, cosine of theta is a over r, tangent of theta is b over a, and so forth. So we can switch these from sort of a's and b's to r's and thetas, or vice versa. First of all, let's do polar to rectangular form. This is going to be something that we're going to do in polar coordinates as well. Same basic idea. This shows up, these basic conversions show up in different contexts multiple times in trigonometry. So here, a over r is cosine theta, so a is r cosine theta. B over r is sine of theta, so b is r sine theta. So if z is a plus bi, some complex number, another way to write that is r cosine theta plus r sine theta times I. Okay, so if you know the r and the theta, you can find the a and the b. If you're going the other way around, the 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 size of this thing, which is done with like absolute value lines, a plus bi is just the r, and that's the square root of a squared plus b squared. Again, Pythagorean theorem on this triangle. The tangent of theta is b over a, so we can use that to find theta. It's just inverse tangent of b over a if a is positive, and pi plus the inverse tangent of b over a when a is negative. So so what's this all got to do with sequence and series? Okay, so we have a form of a complex number that we can take the r and the theta and rewrite the number a plus bi as equal to r plus e to the I theta. So the question is, well, why is this notation used, and why does it make sense with what we know about infinite series? And so we're going to work with this. So remember, for any real number x, any real number that's converged everywhere, e to the x was just the sum from n equals 0 to infinity of x to the n over n factorial. In other words, 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed plus 1 over 4 factorial x to the fourth, and so on. Sine of x is negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial, sum that from n equals 0 to infinity, or in other words, it's the odd numbered terms from the e to the x, but with alternating sign. Cosine of x was the sum from n equals 0 to infinity of negative 1 to the n times x to the 2n over 2n factorial, and it works out like this, or in other words, it's the even power terms from e to the x, but with alternating sign. So remember, that works for any real number. Now, let's say we take this one for e to the x and say now it's true for any complex number z. So now up here, this is x is any real number. Down here, z is any complex number. And we're going to define e to the z to be this sum. The sum from k equals 0 to infinity of 1 over k factorial z to the k, which looks just like this. We just swapped x z in place of x. Here I've worked out what some of those denominators are. So we typically use, x for our generic input for real numbers. We use z as our generic input for complex numbers. So now let's consider what e to the I theta would mean. So we just put I theta in place of the z here. And let's see what that would mean when we work this out. Okay, so let's work that out here. Well, look what happens here. So we got the 1. We got I theta, no, r theta times I. That's fine. If we take I theta squared, that's theta squared, and then you got I squared, which is negative 1. So that's going to change this to a minus. But notice there's no I there. When you cube, we get I cubed, which is negative I, and we get theta cubed. So notice that one goes to minus, but it's also got the I. When we go to the fourth power, we get I to the fourth, which is just 1. So this stays positive, and it's just 1 over 4 factorial theta to the fourth, and so forth. And so what happens is we get, well, it depends on what the power is, right? If the power is congruent to 0 mod 4, you just get the I to the power is just 1, so it just basically goes away. And notice that's a real part. If k is even, but not a multiple 4, congruent to 2 mod 4, then you get an I squared, which is -1. So what happens is on the even powers, look here, 1, uh, -1/2 theta square plus 1 over 4 factorial theta to the 4th minus 1 over 6 factorial theta to the 6th. What do you get? Well, what do you not get? You don't get any i's, right? So those are real terms, okay? So all the even ones are real terms, and then they alternate in sign. So I'm going to group those together as the real part there. And what about the odd power terms? Well, the odd power terms all have an I, but again, every other one is going to be positive, negative. They're going to have an alternating series going there. So when the power is congruent to 1 mod 3, like 1 and 1 mod 4, 1 and 5, for example, then we just get I, and they're positive. But when we get congruent to 3 mod 4, like 3 and the next one would be 7, okay, then you're going to get a negative there. So we put those together and they all have an I. So if I factor the I out of that, we get these two things. So what do we have here? Well, this has no i's in it. It's just -1 to the k over 2k factorial times theta to the power 2k, summing from k equals 0 to infinity. What's this one? Well, it's I times this sum, or this sum times I, whichever way you want to say that. And this is the sum from k equals 0 to infinity of -1 to the k plus 1 over 2k plus 1 factorial theta to the 2k plus 1. Well, if you think about it, this is a real number series. Theta is a real number. So this right here is exactly cosine of theta by this series right up here. And by this series up here for sine, this part right here, in parentheses, this sum, is exactly sine of theta. So what you get is cosine theta plus sine theta I. Now what happens if you multiply both sides by r? So this is e to the I theta is equal to this. It's cosine theta plus sine theta times I. Now if you multiply both sides by r, you get r e to the I theta, which is r times this, or r cosine theta plus r sine theta I. But remember, r cosine theta is a, and r sine theta is b. So an a plus bi is also written as r e to the I theta. That makes sense with the connection that we have to infinite series. So that's the part I thought you might find pretty cool, and see how that connects to infinite series. And one thing that's really nice of this r e to the I theta form is that it makes sense in terms of the properties of exponents and how we multiply things, or multiply, divide, and do powers and roots. So for example, if we have two complex numbers in this r e to the I theta form, okay, where we know, remember, what do these things mean? Remember, the r means that's this radius here, and theta is the angle that we rotate from the positive part of the real axis, the positive part of the x-axis there. So theta is this angle, and of course theta could, it could be rotating around more than once, could be rotating the negative direction. But anyway, that's theta is any real number. So there's theta. Okay, so in any event, this has physical meaning on the graph, just like the a plus bi has a horizontal and vertical change from the origin on the graph there too. Okay, so if you got this r1 e to the I theta 1, and we multiply it by r2 e to the I theta 2, you do it just like you would normally do multiplying something like this. You'd multiply the r1 and the r2, and then these e to the I theta times e to the I theta 1 times e to the I theta 2. We keep the same base and add the exponents. So it's r1 times r2 times e to the I times parentheses theta 1 plus theta 2. Here's an example. 3e to the 2i times 5e to the 4i is 15 e to the 6i. So what happens here is the angles add up, right? And the magnitudes multiply. And division works very similarly. If you have R1 e to the I theta 1 and R2 e to the I theta 2, and you're dividing, then the magnitude is just found by dividing the magnitudes, R1 divided by R2, and the angle is found by subtracting the angles, e to the I theta 1 minus theta 2. So 3 e to the 6i over 5 e to the 4i is 3/5 times e to the, well, 6i minus 4i is 2i. And powers are also easier to work out in this form here as well. If you have r e to the I theta and raise it to some n power, that's just r to the n times e to the I n theta. So if n, I'm thinking of n here as a real number, then this is going to work out and still be in that same form. So 3 e to the 2i cubed would be 3 to the third, which is 27, and then you multiply the powers here and get e to the 6i. So it's really pretty easy to multiply and divide two complex numbers or raise a complex number to a real number power if they're in polar form, although it's easier to add them in the rectangular form. So again, I'm not going to be worrying about this particular section too much in my Calculus 2 class, but I did think it is a pretty cool connection to see how these series that we had worked out in Calculus 2 have something to do with complex numbers and this polar form of a complex number. You may have seen this in your calculus class without, in your pre-calculus class, trig class or pre-calculus, without actually um, seeing it worked out in series. So if you did, now you know where that comes from.